The imine doesn't require a catalyst, but it could use an acid catalyst. So we're going to do the acid catalysis option first. Okay, so this is an imine. The aldehyde or ketone that it's derived from, we simply replace the nitrogen with an oxygen and keep the pi bond where it is. The side product of that would be the amine. The protonation state of this amine will depend on the actual conditions used, but to balance this equation, we're going to keep it neutral. Under acid catalysis conditions, imine hydrolysis starts by protonation to make the iminium ion. So here's my strong acid. The iminium ion is then a stronger electrophile, and so it can get attacked by the weak nucleophile, water, breaking the pi bond towards the nitrogen, giving us a neutral nitrogen and a positively charged oxygen. An overall proton transfer needs to happen here from the oxygen getting deprotonated and the nitrogen getting protonated. There are several options for what could be used as the base for this proton transfer. I'm going to note that if we're doing a hydrolysis reaction, we have water as the solvent. That is one reasonable option for acting as the base here. We can deprotonate the oxygen, which gets us to a neutral structure called a hemiaminal. And then we can protonate using the conjugate acid of the base that we had used. That gives us a plus charge on the nitrogen. The amine can get kicked out by the oxygen lone pair forming a pi bond with the carbonyl carbon. And to consider this reaction balanced, I'm going to switch colors here because this is almost a side note. The acid, if it was acting as a catalyst, we would need to explain regenerating that catalyst by this reaction, which would give us back our HCl. And the ketone would be generated there. Oops, too many carbons. And we have this amine. That's the balanced equation that we drew overall up above. But the problem with this is that the HCl is a strong acid. And so if the reaction was being run in this direction, a stoichiometric amount of HCl, an excess, or at least one equivalent or an excess, would be used, in which case the actual products from this would be the ones that you would get by these curved arrows, either using the amine as the base here. This is what's more likely to actually happen. And so you would get the ammonium ion. Or if you had already shown using the HCl here, you could get to the same place here. So this is or deprotonate the HCl, and that gets you to there as well. So greater than or equal to 1 equivalent of HCl used. In the reverse direction, HCl could technically be the thing that's put in as a catalyst, but what would actually be catalyzing the reaction would be this ammonium ion. So we're going to draw the reverse direction, and we're going to line it up going in the backwards direction here. So here's my ketone, and this is going to be my ammonium ion catalyst. And we will, let's see, I should have one of those hydrogens drawn explicitly so I can deprotonate it. So the first step will be protonate the ketone. That gets us back to the same intermediate that we had above. We have an amine that's going to act as a nucleophile. That gets us to the structure here. This nitrogen has 2 hydrogens on it. There was a mistake up above here. This nitrogen should also have an extra hydrogen. By comparing my structures, I'm doing some error checking here, working in the reverse direction. Okay, so this nitrogen that just attacked has both its hydrogens still. Once I deprotonate, and you'll notice this is a second copy of this molecule showing up. This was the catalytic one. So I'm going to just do a little labeling here. This was the catalytic one. Here it is there. The stoichiometric one that I'm explaining, the one that becomes part of the structure, is this one here. So we have a catalytic one and a stoichiometric one. Okay, so we're going to go ahead and use this to act as the base. That gets to the neutral hemianyl structure. From here, the acid, the conjugate acid of the base that I used, would protonate the OH in order to make it a good leaving group. That good leaving group can get pushed out by the nitrogen lone pair. Which gets to the iminium structure. And gave us a water molecule as a side product here. And that iminium in the final step, if we were using a catalytic base, or a catalytic acid, I mean, this is another copy of my catalytic acid. I'm just going to draw this up in the side margin here so that we can see I had some highlighting. The blue was showing it acting as a catalytic species, and here it is again acting as a catalytic species and getting regenerated back to its acid form. So this was an ammonium catalyzed. All right, to draw the imine hydrolysis under conditions where an acid is not used, we could call these conditions either base conditions or neutral conditions. Or no catalyst conditions. So here is my imine starting material. We have a water molecule reactant. And the first step in hydrolysis without an acid catalyst of this imine is protonation of the nitrogen. If we don't protonate that nitrogen first, then when we attack, we're going to get a nitrogen minus, which is highly, highly reactive. We're going to avoid that by protonating first. So we get to the iminium. And this iminium is going to get attacked by the hydroxide that we just generated. So here's the hydroxide attacking, breaking the carbon-nitrogen pi bond. Giving the neutral structure, the hemiaminal. Before the nitrogen can get kicked out completely, it needs to get protonated again. Again, we can't kick out a nitrogen and give it a minus charge. That's too reactive. So we have water that's present. The water could act as the acid for protonation here. This is a mildly unfavorable acid-base step. But not unreasonable. The pKa difference is about 5 here. Now that the nitrogen is protonated, it is ready to act as a leaving group. Under neutral conditions, neutral or bases around conditions, we should not use the neutral oxygen to push out the nitrogen. Instead, we should think about the fact that this hydroxide that we just generated is going to play a role in the reaction. And so here, I need to draw out my whole OH group. And I can show that this deprotonation prepares that oxygen to push the nitrogen leaving group out. If I had not done that deprotonation first, I would have ended up with positively charged oxygen under conditions where I have hydroxide ion around, which is pretty unfavorable. Okay, so here we are. We've kicked out the nitrogen, we've made the carbonyl, and we are done. In the reverse direction, let's switch colors here again. Let's use blue. In the reverse direction, if we're going to start the reaction, we would simply attack. The amine is a fairly strong nucleophile, and so it can attack an unactivated carbonyl. That provides an intermediate with charge separation, which 2 sequential acid-base steps can take care of. Using a water molecule as the acid, we can protonate the oxygen. And using the hydroxide, that is the conjugate base of the acid I just used, hydroxide can deprotonate the nitrogen. And that gets us to the neutral hemiaminal structure. Before the nitrogen can get kicked out entirely, it needs to get protonated again. Excuse me, I'm thinking about in the wrong direction. Losing track of where I'm going. I am not trying to kick out that nitrogen. I'm trying to kick out the oxygen. So the oxygen can just get kicked out directly. It's not as poor a leaving group as nitrogen neutral would be. Here we go. Kick out hydroxide ion. That gives us the iminium ion. That hydroxide is now available to act as the base. Getting us back to our imine, and that gives us a water molecule. Okay. The next structure is an enamine. The enamine that's drawn here, I'm going to zoom out a little bit so you can see in a bigger picture that the enamine has the same number of carbons in the same carbon connectivity as the imine example above it. And so it actually gives the same products, this pentanone and the same amine. And this hydrolysis reaction would use water as a reactant. And again, we can use acid conditions, or you can call it none, but it's the reaction that is similar to base conditions. We are going to see hydroxide ions in the none example. And we're not going to draw this entire mechanism because we've actually already drawn most of it. We're going to draw just the first few steps here. So, under acid conditions, we would use either an ammonium ion or we could use a strong acid. And we're going to keep in mind that if we're actually using a strong acid, it would be a stoichiometric reaction in the long run, a stoichiometric amount of acid. Whichever acid source we choose to use, we would start by protonating the enamine at carbon 3. So here's 1, 2, 3. Carbon 3 gets protonated by whichever acid we're using. Let's say this is a similar arrow coming down here. And that structure, the result of that has a positive charge on the nitrogen. It has a pi bond. That is an iminium ion. And it's not just any iminium ion, it is actually the same one that we had above. So I'm going to draw some highlighting here. This iminium ion is the same one as our first intermediate here. So we're not going to draw the entire reaction scheme. We're just going to say C above for the rest of the mechanism.